So let's cover a new chapter, okay? Very exciting chapter from inference to training. Okay, we'll talk about distributed training, right? So usually, training deep neural nets are pretty slow and take a long time. And in this lecture and also Thursday's lecture, we are going to learn what are the techniques that can enable us to train neural networks faster. Okay. So in this lecture, we will talk about below aspects. What is the background and motivation for distributed training? Okay, and introduce two concepts. One is the data parallelism. How do we parallelize to use more GPUs to train faster? Okay, two aspects. One is data parallelism. The other is the model parallelism. We either divide the data or divide the model. And we will talk about several distributed communication schemes, okay, to enable us to have a more efficient communication across different nodes. In the first half of the lecture, we are just assuming a single device for inference, but now we have a lot of devices. They have to communicate with each other. So communication schemes matters. Okay, so let's start the journey by first talking about the background. What is distributed training and why do we need that? First of all, before I get started, I want to seek your answer. What is the scenario where in your research or in your daily job or research, have you ever used any distributed training scenario?
I interned at Facebook on the AI team, so the data sets are in sort of the trillions of rows. So in order to train sort of effectively, it's definitely taking place across distributed servers.
Right, trillions of data, so a lot of computation required. Definitely, we cannot fit everything into one node or even one GPU, so we need a lot of nodes.
Yeah, I was cramming for a final project that I didn't budget my time well, but since I trained and distributed, I was able to pick the best one and just use that one.
Distributed, pick the best one so that each one can train faster.
Yeah.
You can collect more. Okay, that's a good point. All right, so as we have seen this figure many times, higher accuracy model usually means we have a lot of computation. And today, these models are getting super big. For example, this GPT-3, okay, that contains 170 billion parameters. And even training this model it is crawled across 8 billion web pages, right? Require 3 million GPU hours if you use just one single GPU, right? So that's probably too long. Therefore, we want to increase the number of GPUs and decrease the hours. So here's a breakdown of several popular models from vision to natural language, okay? From vision models to this BERT, Turing NLG, and GPT-3 models. Okay? And this is the number of parameters all the way up to 175 billion parameters. Okay? And this is the training hours. Less than 50 is relatively affordable, like roughly 1 day, a little bit more than 1 day on this AI100 GPU. Okay? With proper, better library, probably we can do it within 1 day. But with those super big models, the computation requirement and training hours become super long, right? And how do we make it faster? So deep neural nets are notoriously difficult to train. This is quite interesting. The boss asked you, what did you do last month? And he said, train the model for 1 epoch. Oh, okay, fine. What's your plan for the next month? Okay, we're going to train the model for 1 more epoch. So productivity is limited, right? So we want to definitely improve that. So actually, we want to show you a real-world example in our lab for distributed training, how we can accelerate that by using more computation. Right? So if training takes 10 GPU days, if we can use 1,000 GPUs, right, you can possibly finish that in only 14 minutes, ideally. Right? If you divide the time by the number of GPUs. So let's see a real-world use case. So we've been using the Summit supercomputer, right, to train on a lot of videos, okay, to train this temporal shift module video recognition model. So the Summit supercomputer, each node contains 6 V100 GPU, 12 gigabytes of memory, so we can possibly fit the data set locally in memory. Okay? And it's connected by high-speed InfiniBand networking. Okay, super fast. We train this vision model over 660 hours of videos. Okay? Initially, just using one node that takes 2 days for us to train it. Okay? So initially, one node is taking 49 hours and 15 minutes to train the model. This is the accuracy for its action recognition, recognizing what you are doing. Action recognition. With 128 submit nodes, so that's more than 700 GPUs, we can reduce the training time to only 28 minutes. So similar accuracy. But when we scale it to 1,536 nodes, then we can reduce the time to only 14 minutes, okay, with almost no degradation about the accuracy. Right? So we basically turn something that requires 2 days to train. Now it's only a couple or over a time of coffee time, right? Only 14 minutes we can complete the training. So hopefully this gives you enough motivation why we need distributed training and what we can achieve with such techniques. So let's talk about some distributed training basics. Okay? What are the basic techniques? So I'm going to introduce data parallelism, model parallelism, and compare the advantages and disadvantages of these two parallelism. Okay, so let's brainstorm a little bit, right? We have a huge model, a pretty big machine learning model, contains billions of parameters. Okay? And secondly, we have a huge amount of data set, many hours of videos, or even millions of web pages of text. What are the possible ways to parallelize these models and this data? And how can we train it faster?
Which is a different batch of training.
Right. So we can first of all on each GPU we train different batch of data set. Right. So here we color the data set into 3 different colors. GPU 1 trains on this blue image. GPU 2 trains green batch, and GPU 3 can train on this yellow batch. Right? That's a good point. Right. So this is data parallelism. We are distributing images across different GPUs or different nodes. So different node, they are training on the same training on the same model, right? Same model, but different data, right? So just distributed data. Okay, so this is called data parallelism. We split the data set into different chunks, and each GPU just train on a particular chunk of them, and they share, okay, the same model across different devices. Okay. And there's another mode which is called model parallelism. So rather than dividing the data into several chunks, we can also divide the machine learning model. Okay, so say this is a super big model that has 4 stages. We can split the model across different GPUs. Okay, so using a single copy of data, but pass the first chunk of neural network to GPU 1, the second chunk to GPU 2, and the last chunk to GPU N. Okay, so in this way, each GPU is responsible for a portion about this pipeline. So what is the potential issue when we are trying to divide the model in this way?
You can be bottlenecked if one GPU is really slow. The weakest link basically coverage of throughput.
Yeah, exactly. Say they depend on each other, right? In order to finish the whole training, all the GPUs has to finish at the same, right? So if GPU 2 is super slow, or we allocate a super large chunk, or this chunk is taking a lot of computation, it's hard to load balance. Right? Okay, so this is the animation. We just divide the model, different chunks of the model to different GPUs to parallelize them. Okay. And now let's compare the advantage and disadvantage of this data parallelism versus this model parallelism. Okay. So data parallelism, we split the data. While the model parallelism, we split the model. Okay. And for data parallelism, we have the same model, okay, and replicate that across different devices. Well, for model parallelism, we have to move the activations. Okay, the output of the first GPU will be the input of the second GPU, so we have to move those activations. For data parallelism, it's relatively easy to parallelize, since for image, we can crop them, resize them to the same size, same dimension. So the workload across different GPUs are roughly similar. 2 images for GPU1, 2 images for GPU2 in this figure, right? But model parallelism is hard to parallelize because different parts of the model might contain different number of parameters, different flops. It's hard to do load balancing. And data parallelism requiring copying the model by n times if you have n GPUs, right? So there's some redundancy. This one will fail if the model is so big, right? Even one GPU, you cannot fit the entire GPU, right? So that would require this model parallelism, where you have to divide the model into several chunks, and each GPU will be responsible for only one chunk of the model.
So you synchronize backpropagating the gradients when you do data parallelism. Like it seems like if one of them finishes and wants to do the backwards pass, do the others just have to wait until they're done and then do the backwards pass with that one's gradient? Or?
Right. So there's synchronous training and there's also asynchronous training. The widely used is the synchronous training, where different GPUs gets allocated with different chunks of data, but they're of the same size or same workload. So the flops, the workload they get allocated is roughly exactly the same. But you know, computers they have different. They may be different. They may differ a little bit. Some may complete the job earlier. Some of them may get stuck in the middle, context switch, etc. So the slower one has to wait for the faster one when they are doing synchronization. And later, people try to challenge this assumption and experimented with asynchronous training and find actually asynchronous training also make the model can converge even without synchronization. So that's the magic for deep learning. You can prune the model, you can relax the synchronization, you can relax all sorts of things that conventional computer science is assuming that's something mandatory. But actually a lot of requirement is not mandatory. Sometimes we even find, actually in the next lecture, we can prune, aggressively prune those gradients. We can throw away those gradients. We can also take those stale gradients, like the gradients coming from 2 or 3 iterations ago. So for using those techniques to relax for the bandwidth requirement and also tolerate the long latency. All right, so next section, we are going to talk about in more detail about this data parallelism. Okay, so understanding the distributed training workflow and system design challenges. Okay, so this is the basic setting for distributed training with data parallelism. Okay, so we can scale the training across multiple machines. Okay, each machine may have 4 or 8 GPUs, right? And each of them has a private copy of data. And we have a centralized parameter server, okay, which is the central controller for the whole training process. Okay, so this is just one of the possible setup with a centralized setting. And then we are also going to talk about this decentralized setting. Okay, so there are 2 different roles in the framework. We have the parameter server, okay, who is responsible for receiving the gradients, okay, from the workers, and also send the aggregated weights to each worker. Okay, and we have several workers. They are responsible for computing the gradients using its local copy of the data set. Okay, and send the gradient to the centralized server. And here we make it animation to have an overview of this infrastructure. Okay, so we have a neural network model of gradients on the parameter server, a centralized parameter server. And then we have 4 workers in this example. Okay, so we have a pool of worker nodes. Each can compute their local gradients. They have a local replica about this neural network model. Okay, and they have each of them has the same amount of training data. Okay. So we split this training data set equally by 4 chunks across these 4 workers. Okay. So to begin with, we replicate and pool from this parameter server, and pool the parameters of the neural network to each worker. Okay. We have replicated exactly the same neural network model. Say if it is resonant 50, then we have like 25 million parameters. So each model, each worker has exactly the same copy of this 25 million parameters. And now we are dividing the training data set. Say we have 1 million images, like an ImageNet, we have 1 million images. Then each node gets a 250,000 images, right? A 250,000 images as its training data. And then each node is going to compute the gradient over these 25 million parameters on its own training data and calculate a local gradient. And then it's going to push the gradients to the centralized parameter server. Sum up, the parameter server is going to sum up all the gradients and then update this global model, okay, using the weights that has just been collected and summed up. The next is going to replicate, and each node is going to pull an updated copy of the neural network model from this parameter server. Okay. And then we are going to just repeat this step. We replicate the model across different workers, split the training data, and then compute the gradients on each node, and then push the gradient updates to the centralized parameter server, sum them up, and update the global model. Okay. So this is the setting for data parallelism. If we look at the pseudocode, this is a single node training scenario, right? We sample a subset of the data, compute the gradients over this chunk of data, and then perform this gradient update, W minus learning rate times the gradient. For distributed training scenario, we added 2 lines. So for each worker, we have to first pull the gradients, pull the weights from the parameter server, pull the weights from the parameter server, and then sample the data from the data set, compute the gradients using its own local copy of the weight, and then push the gradients to the parameter server. So for a couple of workers, it's probably fine, but if we have a huge amount of workers, a super big amount of workers, the communication overhead will be quite large, right? So the bandwidth requirement for this parameter server grows linearly with the number of workers, right? So imagine you have n workers, you have to collect n copies of data, right? So that's why the bandwidth requirement actually grows linearly with the number of workers. So let's use pencil to calculate what is exactly required for a simple example using resonant 50. Right? So resonant 50 has about 24.4 million parameters. Okay? So how many megabytes is that? Each parameter contains 4 bytes, assuming 32-bit. Right? So that's requiring roughly 97.5, about 100 megabytes of storage. So that's the number, the size of the weights. What is the size of the gradients? that needs to be sent and received in this case. So we have this amount of weights. What is the size of the gradients? Yeah, basically the same, right? The dimension of the gradient is exactly the same as the gradient as the weight, right? So we have to send and receive roughly 100 megabytes in every iteration, right? So with a batch size of 32 on this 20 pi CPU, it takes about 3 iterations per second, right? So multiplying them together with 256 nodes, imagine we have 256 nodes connected to the centralized parameter server, how much communication bandwidth do we require? Just multiply them together, right? We have to receive and send and receive across 256 nodes, okay? 3 times per second, okay? And each time we have to communicate about roughly 97, roughly 100 megabytes. Okay? Multiply them together, boils down to 73 gigabytes per second of communication bandwidth. That's actually pretty huge. Even the Mellanox feedback, the bandwidth is as big as like 12.5 gigabytes per second. This is already very high-end networking infrastructure. Okay, so we do need to perform distributed training without this centralized server, right? We have to decentralize this training across different nodes and reduce the bandwidth requirement. Otherwise, the centralized parameter server will soon become a bottleneck due to limited communication bandwidth. Okay, so how do we achieve that? So let's talk about distributed communication primitives and talk about how do we get rid of the centralized parameter server and purely do the training in a decentralized manner, where just before we dive down into details, so let's first brainstorm together, how can we get rid of this parameter server? And is it possible to do something in a decentralized manner? Give you maybe 2 minutes to think about it. Feel free to propose some new ideas. Maybe look at this figure, parameter server versus several workers. Now we don't have this parameter server. And how do we still keep this overall system updated?
Could a node just publish when it's done with a batch to all the other nodes and say, yeah, done, here's my gradients, let me know when you're ready?
Yeah, every node can announce, okay, I'm done. This is my gradient. Feel free to grab my gradient. Yeah, that's one way of doing that. Everyone just broadcast.
I was gonna say we can like everyone sends to like a few neighbors that like in some like it goes in some words that like one server is saying that every single sense like that. Because I think if every node broadcast is gonna have the same bandwidth problem. So you probably only want to like send to one or two other servers.
Yep, that's a very smart improvement rather than broadcasting one to everyone else. We just selectively maybe just broadcast to my neighbors, and my neighbor can talk to his neighbor or her neighbor or its neighbor, and then soon everyone gets broadcasted. Right? Yeah.
You broadcast it to all the nodes that are layers above.
Oh, that's a hierarchical setting, right? You can set a hierarchy, say like in our classroom, we have 3 rows of students, right? First, row 1, these 4 students communicate with each other, exchange the gradient, and then row 2 exchange the gradient, and then row 1 communicate with row 2 communicate row 3, in such a hierarchical manner. And that's another good option.
And I think it's actually a max degree and mean degree problem.
So in this topology, the max degree in this graph will be n minus 1. And you want the degree in this topology to as average as possible. So you can use a ring to store all the weights, and when a node computes the gradient of its neighbor's weights, it can broadcast the gradient to its neighbor.
Setting up in a ring-based manner,
Yeah.
so that we have
So every
only
node
two neighbors, only two outbounds. Yeah, there are ways to do that in a ring or reduce. Let's have some idea.
Another reality is to divide a set of all nodes into different clusters. And for each of those, you can do different strategies, say arbitrary loading, to update node with less. You can update less frequently, such that you won't have the overall gradient
Oh, so not update all the select all the gradient traffic, but selectively pick some of the more trustworthy ones, assuming some of the machines are more faulty than another. And you can selectively, that might be helpful for the heterogeneous setting where we have both old GPUs and also new GPUs in the setting. And old GPUs tend to be laggy and sometimes more faulty. So we can have some consensus mechanism. Yeah, those are super good ideas. So let's see what we offer in the lecture. So let's first introduce several communication primitives. Primitives are basically the fundamental operations. So point-to-point communication, which is the simplest. Just one talk to another, like node 0 talk to node 3. I want to send something from node 0 to node 3. Okay, we have this receive primitive, which is just receiving something from node 3 to node 0. Okay, so this is point-to-point. Okay, I've implemented in Salted MPI. NCC a lot of frameworks. Okay, as one of the basic primitives, just point-to-point send and receive. We also have this collective communication primitives, which is scatter and gather. Okay, say I have I have 4 apples. Okay, I have 4 apples. I want to distribute one apple 1 to the first kid, and apple 2 to the second kid, and distribute one apple to each kid. So each kid has 1 apple. And we can also gather, right? So after they eat the apple, they have probably some gather their maybe their feedback, right? So we can formulate a array which number 0 is coming from node 0, element 1 is coming from node 1, and 2 is coming from node 2. Okay, so in this mechanism, we can use scatter-gather operations to either disseminate some of the your array or collect the array from different parties. So very similar to gather, we also have this reduce primitive, which is very helpful. Okay? So different from gather. Okay, let's take a look at gather. We just collect each element, okay, from different node and put them together as a new tensor, right? So different element of tensor is coming from different nodes. But in this reduce operation, we not only collect those elements, but also we want to sum them up together. Okay, so that's why we are writing that in this way. Still is one element, but it's a reduced version. We can either finding the max, we can sum them up together, right? So this is the difference between reduce and gather. Okay. We can also do this all reduce operation. So previously, node 0 collected the information from node 0 to 3, but now we want all the node to collect the information from all the other nodes. This is exactly like I just mentioned, right? So each node sends the information to everyone else, and everyone is collecting the information from all the other nodes. sum them up together, right? So collective performance communication patterns across all the workers to reduce is similar together by either averaging or summing during this aggregation. Let's see what type of communication scheme is used. For example, in this replicate and pool. Okay, so we're pulling the weight from this parameter server. So what kind of primitive do we need to implement this pull and push? Are we using scatter or gather or send or receive? Okay, so we can use this send primitive for pulling, right? So we send the parameter server is going to send the weights to different workers. Okay? And for push and sum, we can use this reduce operation to average from all the workers. Okay? Average from all the workers to this parameter server. So we can use this reduce primitive.
So the difference between send and scatter, that the scatter, you're sending like a different message to each of the end nodes that you're sending it to,
Right.
or is it
Different, yeah, that's
okay, so
the
that's
key
why
difference.
it's send, not scatter.
Right, scatter you have basically for different components. It's going to be distributed to different workers. So you have an array divided into 4 chunks. Chunk 0 go to node 0. Chunk 1 go to node 1. That's different different elements.
So it's more like scatter for the data, model is send.
For send the data, each piece of data is actually different. For data parallelism, the data is actually different. Right? So here we are sending the model. We are sending the same model from the parameter server to different workers. So that's why we are using send here rather than using scatter. Scatter, you are scattering different elements. But here we are sending the same model across different workers.
Is the main server averaging all the information coming in so that it's not just like overwritten, so that it's like all the information?
It's going to reduce to collect the gradient from each server, okay, and will reduce by summing them up and update the model using the averaged gradient. Okay, so in this case, what is the bandwidth requirement for each node? For the pool operation and also for this sum operation. Assuming we have n nodes, n is the number of training workers. For the sake of time, for the worker, right? So we just need to a bandwidth of 01, right? Since we have only need to receive one piece of model, but for the parameter server, it is responsible for delivering, for sending n copies of the model to each worker. For push and sum, similarly for the worker, I only need to receive one of them, but the parameter server needs to handle n servers. So the parameter server is clearly the bottleneck for this bandwidth requirement. Okay. So we want to perform aggregation without this centralized server, okay, using this all reduced mechanism. Okay. So exactly like just now we discussed. Now we can get rid of the parameter server. There's only 4 workers nowadays. There's no centralized server, and each node is responsible for sending the node to 0, to node 1, node 2, to node 3. Okay, and each node, for example, node 2, is going to use this all reduce operation so that we can collect the gradient from each of them. Okay, and finally sum them up or average them. So in this case, the time requirement is on n. Okay, we have to perform n steps. Okay, and the bandwidth requirement is also on, since at each time step we have to send n copies of the model. Okay, so this is the naive or reduced implementation, which is sequential. Okay, 4 nodes, we have to use 4 different steps. Okay, so time is long, it's O(n), but this requirement is also pretty big. Therefore, we have exactly the second approach, which is rather than communicating to everyone else, we can just communicate to our neighbors. Right? So in step 1, node 0 talk to node 1, node 1 talk to node 2, okay? 2 talk to 3, 3 talk to 1. Okay? So after that, node 0, okay, we'll have both this green copy of the weight and also the red copy of the weight. And node 1 not only has its own color, which is yellow, but also has node 0's weight. Okay, so that's why we have both green color and yellow color. And after this step, okay, node 0 will also get red and also blue. So that's why it's having 3 colors now. And node 1 now has both this yellow, this green, and then this red. So it is 3 colors. And then we do another step where one only talks to its neighbor, right? So finally, node 0 has all 4 colors, indicating it has successfully received the information from all different nodes. Okay? The difference for this method is that not everyone is talking to everyone else, but one is only talking to its neighbors. Okay? 0 is only talking to 1, and also 3. Okay? It's sending to 1, receiving from 3. Node 1 is only sending to node 2 and receiving from node 0. Okay? So that limited the amount of traffic. So for timestamp, that's still O(n), right? Since we have to do O(n) steps. But what is the bandwidth requirement now? It's only O(1), right? Since I don't have to talk to all the other nodes, but I only need to talk to my neighbors. Okay. For example, I only need to send from I to I+1 and receive from I+1 to I. So the bandwidth requirement becomes constant. Even though I can increase from 4 nodes to n nodes, I still only talk to my neighbors. Right? So that's why we have O(1) bandwidth requirement. Okay, so now we have another scheme. Previously, for this naive, we can also do this or reduce operation in the parallel manner. Okay, so remember in this slide, we are dividing that into 4 different steps. Okay, each step we serve only one node. Alternatively, we can do this parallel reduce. Okay, so at the same time, we just use all the reduce happen at the same time. Therefore, we have O(1) time complexity. But however, the bandwidth requirement is bigger, right? So O(n) square bandwidth requirement, which is worse. So this is a summary. What we learned so far using parameter server, okay, using which has O(1) time complexity, and peak node bandwidth is also O(n), which is the bottleneck. And we also propose this all reduced method as a baseline. Okay, both of them are slow, and then we can improve that by using this ring all reduced method. Okay, so we can reduce the peak node bandwidth to O(1), or we can use this parallel all reduce that can reduce the time to O(1). But can we do even better, right? So let me introduce this recursive halving all reduce. Say currently we have 8 nodes, right? Using different color to represent each node. And ideally, we want to have each copy to have all the information across everyone else, right? So the first time step, each node just exchange with neighbors, okay, with offset of 1, right? So after that, node 1 has both green and red, okay? And similarly for the remaining nodes, it's 2 colors since it's exchanging information with its neighbors. Next step becomes interesting. Each node exchange information with neighbors with offset of 2. Okay, so in this case, we have green and red, and also red, this light red and also blue. Okay? So after that, we have 4 colors for each node. Right? But for this one, we have green, red, yellow, and also blue. Right? So green, red, yellow, and blue. We have 4 colors. Then what shall we do for the step 3? 4, right? So each node exchanges neighbors with offset of 4, exactly. So in that case, I'm going to communicate with this node. So this dark color versus this light color, and also exchange information, where each node has both, actually all 8 colors in only 3 time steps. Okay, so this is like a tree structure. In log n depth, I can quickly get all the information from all the nodes. Okay.
Isn't that, the bandwidth isn't the same at each step, though, right? Like, for the first step to the second step, we do twice as much data transmission.
So amount of 1, 2, 3, 4. Right? Here you also have 1, 2, 3, and 4.
Oh, it's not, you're not communicating 2 tensors in step 2, meaning like that's only 1 tensor, we've already averaged it.
Yeah, this one you already averaged that.
Got it, okay.
Yeah.
Would, in the first 2 nodes of step 2, would it not be the same average?
Which one? These 2?
In step 2,
Step 2.
the ones with the same color, or is that not the same?
They are, let me see. This one, they are of the same value actually, since both of them are averaging with each other. Yeah. So this is a very smart way, right? So this is making the all reduce actually happen, finish within log n steps, called recursive halving or reduce, also called butterfly, since it looks like a butterfly or reduce. So let's put them here. So using this recursive halving, we have all log n time complexity repeat. Node bandwidth is only O1, right? Since I'm either communicating with my direct neighbor or neighbor with distance of 2 or neighbor with distance of 4, rather than talking to everyone else. Right? So the total bandwidth requirement is On in this case. And this is very widely used method nowadays. So far, we talk about this data parallelism, right? So in several scenarios where we might be training a super big model, where even 1 GPU cannot fit the model. Say a popular model actually we are actually working on is this OPT model for super big language models, right? Okay. Parameter wise, it contains 175 billion parameter. So if each parameter is represented by even by float 16, not to mention float 32, right? So how many storage is required? So 2 bytes, so 16 bits are 2 bytes, right? So 175 billion parameters multiplied by 2 bytes, that's altogether 350 gigabytes of storage is just required to simply store the model, not to mention the size of the activation, right? So this is a huge chunk of memory storage requirement. So the largest GPU memory we have on A100 GPU is 80 gigabytes. Okay, so by no means we can fit just even the inference on 1 GPU for such a big model. Right? So with 80 gigabytes, we need at least 5, right? Those GPUs in order just to host the model size, right? So this is one scenario where data parallelism is not enough. Okay, we have to parallelize to divide our model across different GPUs. Okay, so this is the setup. Okay, assume we have 8 GPUs. Okay, we are dividing the model, different parts of the model to different GPUs. Okay? And they share the same data either for training or for inference. So if the total storage requirement is 350 gigabytes so the total size of the weight is 350 gigabytes, then divided by 8 cars, each car is responsible for roughly 44 gigabytes of the weight. Okay, so that we can replace and train successfully on the GPU. So let's see, how do we enable such communication across different GPUs? Imagine this is actually not as simple as data parallelism, right? For data parallelism, each node or each GPU has a unique copy about the whole model, right? So it can do its local update. However, for such model parallelism, I only have partial 1/4 of the total model, right? So in this case, I divide the model into 4 different chunks. Okay, so node 0, GPU 0 is responsible for only 1/4 of the model. So all the nodes have to work together in order to complete one step update, right? So this is the forward, okay, noted by F. On GPU 0, I do F0. On GPU 1, I do F1. Okay, so until the last part of this model, it's completed by GPU 3 in this case. So this is forward. And then we have to do the backward. Okay, so we have to do the third chunk on the third GPU, and then the second chunk on the second GPU. Okay, so actually, from the timeline perspective, okay, we first do the first do the inference to the forward from node 0, and then that handles the activation to node 1, and then node 2, and then node 3, right? After this forward completes, we do the backward, right? For B3, B2, B1, B0 in the reverse order, since we are doing back propagation. So each counter represents each node or each GPU. Okay. So what is the problem for using this setup to do model parallelism? Think about the utilization.
So doing nothing for the majority of the time.
Exactly. So idle, right? So this node 0 will be idle for this time until the last time step. Right? Super low utilization. Right? So if we see that different layers, forward and backward, and actually all the bubbles means the GPU is being idle for the entire time step. So if you have taken 6004 computation structures, you might be familiar with such pipeline diagram. Right? So this bubbles is causing the utilization problem. So how do we improve that? So actually, the theoretical utilization is only 25%, which is pretty low. So we can do better by actually doing the pipeline parallelism by further dividing the input data into several chunks. Okay. For example, we can split a single batch to several micro batches. For example, this is the dimension of the original tensor. We have a batch size of 16. Now we are going to split it by 4 chunks. So each chunk has only a small batch size of 4. Okay? And let's see what happens to the utilization in the new scenario. So as long as F0, this is the first GPU, this is the second GPU. As long as the first GPU completes the first chunk of data, right, it can immediately push the activation to the second GPU. So the second GPU can start working on the first batch of data. At the same time, the first GPU can start working on the second batch of data. So in this steady state, GPU 0 is working on the fourth chunk of data. GPU 1 is working on the third chunk of data, etc. Right? So at this timestamp, all the GPUs are busy. Okay? This is ramping up, this is winding down. Okay? And for the back propagation, after this is GPU 4, okay, completes the last chunk of data, we can start from forward to switch to backward, right? And as soon as finishes the backward of this is the first chunk of data, right? This is zeroth chunk of data. It can handle the back propagate to the third GPU and the second GPU and the first GPU, on and so on, right? So now we have this overlap, and utilization becomes higher, right? You can see the bubbles in this diagram is significantly smaller than less amount of bubbles than the first one. So we improve utilization from 25% to about 57% in this case. That's about 2.5x improvement. Okay. So to summarize, the solution is to divide the training data into several chunks, okay, so that we can use this pipeline parallelism to do such model parallelism. So let's do some performance analysis for this method. Okay. K is the different partitions, okay, and M is the number of micro batches. Okay. So K can also mean the number of nodes or GPUs. Okay. We can see that as we increase the K, okay, from 2 to 4 to 8, in general, it's increased as we increase the number of GPUs, the speed becomes faster for both region and also NLP tasks for scenes and transformers. And also, if we increase M, okay, subdividing the data into even smaller chunks, the performance also increase. Okay, increases the amount of utilization. So with reasonable M and K, there's almost a linear speed up when training transformers. Okay? So with 8 nodes, we can achieve 6.3x speed up. Okay, so beyond the model parallelism, what if so far we assume each layer can fit the GPU memory? What happens if even a single layer is too large to fit the memory? Okay, so we need to not only split the model, but also we need to further split the layer. Okay, even one layer, we have to split it across different GPUs to get this tensor parallelism. Okay, so not only this model parallelism, but finer granularity, we have this tensor parallelism. So this is comparing this model parallelism versus tensor parallelism on this computational graph. Okay. So this is the first layer. We are dividing the model by different layers. Okay. Layer 1 on the first GPU, layer 2 on the second GPU. This is the model parallelism we just described. In another scenario, we can further divide the tensor. Right? This is the weight tensor. This is the activation tensor. We can divide them by two different colors. Okay? So we can further make fine-grained parallelism in the tensor's granularity across different nodes. Okay? Blue one is one device. The red is another device. Therefore, we can have a hierarchy of different structures, different parallelism granularity. Right? We can have either the tensor parallelism. We can also have this model parallelism. And also automatic means we have to find the automated approach to determine how do we divide the model into several chunks, right? Ideally, what is the requirement for a good practice of dividing the model or dividing the tensor to improve the utilization? What is a good practice? What is a bad practice? Imagine we have a model that has a lot of computation on this layer, very little computation on the second layer. If we divide in the middle, what happens? Load imbalance, right? So we want to ideally divide the model or divide the tensor so that each GPU has roughly the same amount of workload. So when we are doing pipeline parallelism, each of them is roughly having the same amount of workload, right? But do that manually is very challenging, right? So people want to have this automatic approach. So Alpine is a very awesome work that can handle these 3 dimensions at the same time. For example, given this entire pretty big search space, the dashed line is actually dividing the layers. Okay? Chunk 1, chunk 2 into 2 GPUs. The different color within the dashed circle is indicating tensor level parallelism. We are further dividing the tensors. Okay? We can divide 2 by 2 versus 1 by 3 or 3 by 1, or 2 by 2 this way. And so pretty big in design space. So alpha proposes hierarchical space. And first, doing this inter-operator parallelism, and then this intra-operator parallelism into hierarchies. Given this example, we can divide it in many different ways, right? But apparently, is this better or this better? This is better. Each color indicates a different stage. Will be put on a different GPU. This one is inconvenient because of the communication is twofold, not only here, but also here. Yeah, that's one point. The first one is more attractive because the interface between the different stages is more clear. Are there drawbacks for this approach? Right. 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 This node might suffer from starvation since there's very little workload compared with this one. Well, the other argument is that this approach has two more dependencies, right? So synchronization and communication bandwidth might be larger using this approach compared with this approach. Okay, so we have to search. It's not straightforward to determine which one is better. Each one has its advantage and also disadvantage. So we need a systematic search approach to figure out automatically which is a good approach. And also for the intra-operator parallelism, there are many different ways to subdivide this matrix multiplication. For example, we can divide the A matrix, which is activation, and B is the weight. We can also divide the weight. Okay? So divide the max-mal into two parts. Okay? We can also divide both A and B and do the outer product. So this blue part will be multiplied by this blue part, get a partial sum, and finally we are going to do all reduce to a reduction for the different partial sums. So there are also different methods to explore for the intra-operator parallelism. So for both inter-operator parallelism and also this intra-operator parallelism, there's a pretty large design space. So in this work, they propose to do them step by step. First, do the inter-operator paths and the intra-operator paths, and have the cost estimation for each of them, and finally propose a runtime orchestration. And it's showing pretty good results, showing this actually matching this manual systems, those carefully designed manual methods for this GPT model up to 39 billion parameters with 64 GPUs. And also compared with a different model, actually outperformed the manual design by up to 8x for the MOE model. Okay. All right, so let's summarize for today's lecture. Right, so we learned that the basic concepts of distributed training models are getting pretty big. Many GPU years if we just use a single GPU. Therefore, we need different parallelism. Okay. One is model parallelism. The other is data parallelism. Okay. We first introduced data parallelism. So for each GPU, it's going to be training on different set of training data. Okay. But they have exactly the same copy of the model architecture. Split the data for data parallelism. For another scenario where the model is too big, even the whole model cannot fit a single GPU, we need to split the model. Okay? Different GPUs is responsible for different part of the model while they are sharing the same input training data. And we discussed about this bottleneck of scaling is basically the communication bottleneck, right? From a couple of nodes to many different nodes, the overhead of communication really becomes the bottleneck. And we propose several techniques to remove this communication overhead by using this decentralized training method. Okay? especially such recursive halving or reduced manner that can complete the reduce in log n steps. Okay? This is distributed training without parameter server. And finally, we talk about this model parallelism, how to improve the utilization by subdividing the data into smaller chunks, okay? So that we can use such pipeline parallelism to improve the utilization of each worker. And here are some references. And in tomorrow, in Thursday's lecture, we are going to talk about other techniques that targets removing such communication overhead by gradient compression and also delayed update. Right? So we talk about model compression. Now we are going to introduce techniques actually done by our TA Yujun. He's finding that actually we can very aggressively reduce the communication. In every 1,000 gradients, it's enough to only communicate one gradient and throw away the remaining gradients, or even quantize the gradient to only 1 bit and only communicate 1 bit, and that's enough convergence. Okay, so looking forward to the next lecture, and that's all for today.